dodging at the point. It's all right. Okay, so we have 2 chapters left, which is 2 more types of inference. The chi-squared test, the chi-squared model, it says it tests hypotheses about categorical variables. So everything we've done so far has been not categorical variables, quantitative variables. Do you remember what is a categorical variable?
Like color.
Color, yeah. It just counts how many are in a category. A category is like a label or a group. And so like what we did yesterday when we counted up how many red, blue, green, whatever, Fruit Loops and then M&Ms. That was categorical data because we were just counting how many of each color. Got it? Okay, so they're also called, somewhere it says this, counts, because again you're just counting how many are in each category. Okay, so just like our other statistical inference methods, we have a special kind of curve, and you don't have to get this out, but it's called the chi-squared curve. So it's kind of like the z and the t, but it's not very normal. It says it's skewed to the right, and as the degrees of freedom increase, the curve is less skewed. So it's the last chart on your orange table in the very back. It says chi-squared. See how it's skewed to the right? Mm-hmm. But other than that, it's kind of like the normal model. The degrees of freedom as they increase, the p changes, and we'll look at that just a second. So easy enough. So you have conditions like always. The first one is just that it has to be counted data, or the thing you need to watch out for when you start having to pick out which test to do is it has to be categorical. If it's not categorical, you can't do it. One? Yeah. Well, that worked out. Okay. The next 2, I don't know why these are in opposite order, but they're really the same conditions we've been checking, as always. A random sample, that's usually what we check first, so that still has to be true, or unbiased and representative, and it still needs to be less than 10% of the population. So those 2 conditions are the same. The last condition is the one that's always different on all the different tests that we've done. And it says it has to be a large enough sample. This one's really easy to check. You don't have to make any histograms or see if it's normal. It just says at least 5 in each case. So that's all you have to do is make sure that there's at least 5, that they're called expected values in each case. So the conditions are really easy to check, finally. Any questions so far? All right, we're going to move pretty fast then. So it says there's 3 different chi-squared tests, but they all work very, very similarly. The first one's called the chi-squared goodness of fit test. So you're going to just basically see how well goodness, it's a weird word, data fits an expected model. So it asks when will we use this, and that's exactly when. So when we're trying to determine if a sample fits what we expect. So then we're trying to determine okay, all kinds of mistakes. When we are trying to determine if a sample fits an expected distribution. Okay, so yesterday when we looked at the M&Ms, we had what the company told us, what percent they said were green, what percent they said were brown. So that's what we would expect to see in a sample, because that's what the company says they make. And then we had our one sample, we were trying to see how well it fitted what we expected. So that's why you use or when you use a goodness of fit test. So your hypotheses, these, if you have to write these in works. There's no way to write them in symbols. Okay. First of all, I'm going to write them in general what it should be, but you should always put them in context. But basically the null hypothesis is that your data or your sample does fit the expected distribution. And then what would the alternative be? Does not. Yeah, it does not. Okay, and then just like any test, we're going to get a test statistic and get a p-value, and then decide whether to reject or fail to reject the hypotheses. Okay, so the test statistic in this one is not your z-score, it's not your t-score, it's called chi-squared, and that's what we practiced doing yesterday. So I'm just going to rewrite the formula for chi-squared. Okay, so I made you do a few yesterday, but of course you can use your calculator, and that's what we're going to look at how to do today. But I will show you when we use our calculator, in order to get full credit on the AP test, you have to still show a little bit of the formula. Usually they say if you'll just show the first two terms, that's enough. I'll show you what I mean by that. It's not hard. Then you can use the calculator, and then that's usually more accurate anyway. Any questions so far? I'm not giving you anything crazy. Okay, so then the last thing you'll do is find the p-value, and you can use your calculator for this too. It says that the larger chi-square value equals a smaller p-value, and you know that the smaller the p-value is, the more likely are you to reject the null hypothesis. So there's two ways to do this. I know which way you're going to pick, but I'll go ahead and tell you both ways. The first way is that you can use your table. And I'm going to show you using what we did yesterday. But all you do is look up the chi-squared value that you calculate, and then you find what's called your degrees of freedom, which we've done before. The degrees of freedom is n minus 1, which in this case, n minus 1, n is the number of categories that you have. And I'm going to go and show you this anyway, even though most of the time you're going to use a calculator. Occasionally there's multiple choice questions where it'll just give you the chi-squared and ask you to find the p-value. And so you have to know how to do that, either by hand or using the table. So this is the question about the fruit loops that we did yesterday. There are how many categories in this one? 6. So what would our degrees of freedom be? 5. So if I ask you, we could have done this yesterday, but if I ask you to find the p-value, we ended up with a chi-squared of 9.41. There's 6 categories, so the degrees of freedom is 5. And then it works like the t-table. You just make sure you're on the chi-squared table. This just makes my hand look really scary. You see that? Yeah. It's like alien. Go to 5. And then you kind of have to just look in the middle and see what your chi-squared is closest to. Like that says 9. Can you see that? It says 9.24. So ours is a little bit higher than that. So our p-value would be a little bit below 0.1. So probably like 0.9, 0.09, or 0.08. Okay, that's all you have to do with the table, which you probably won't do. But I thought I'd show you anyway. So second method is to use the calculator. So it's called the chi-squared GOF, fit test. Unless, a couple of you yesterday, I had to download a program to your calculator. So yours is going to be slightly different, but it will still do all the calculations for you. The first thing you'll have to do is make two lists, L1 and L2. The L1 has to be your observed values, and L2 has to be your expected values. If you do them backwards, you'll get the wrong answer every time. So that's important. Okay. Ready to try some examples?
So in my calculator, it's just x squared, chi-squared test. Is that?
No, that's not the same thing. Did
Okay.
you have your calculator yesterday?
Yeah.
Is it 84?
83.
Okay, I need to give you the program.
Okay. You want it now?
Yeah. Okay, let's try some examples.
Yeah.
Got it. Okay, so go ahead and read this first problem about New York. Have the racial breakdown of this. Okay, so our question says, do the police officers, so you have different percentages, the ratio of different races for the police officers, and you're trying to see if that reflects the ethnic composition of the city. So this is what is expected. We're trying to see if the police officers have the same, about the same ratios as the city. Okay, so first thing I do, write our hypotheses. So you have to do it in words. The null hypothesis is that always that it does fit what it's expected. So we have to put it in context. So our null hypothesis would be that police officers, yes, do reflect the ethnic composition of the city's youth. I'm just restating it. Okay, so that's what we expect. And so what would my alternative be?
They do not.
Yes, so police officers do not. Okay, so next step is calculate the expected values for each category. And that means these are counts, so we don't want percents. We want actual numbers. How many do we expect to be in each category? So, start with, I guess, the white. Okay, so we're looking at the police officers. There's 26,181 police officers. If they do reflect the ethnic composition of city's youth, then how many, or how can we figure out how many we expect to be white? We're saying that we expect them to be the same as the under 18 population. So how many or what percent under 18 are white? 29.2. So if this was true, then 29.2 of the police officers should also be white. So how can I figure out 29.2 of 26,181 is. You know how to do that. Yes. So that's all you get to find the expected value. Okay. And I don't think I did that right.
I think I just canceled that thing.
Oh, yeah.
No, it's still there.
Is it here?
Yeah.
Would we leave it a decimal?
You can leave it as a decimal, even though that may not make sense, but because it's a hypothetical situation, you can have a decimal. It's what you expect. But obviously, in real life, you couldn't have 0.85 of a person. Okay, and then you just keep doing that for every category. So let's see, 28.2. Oops, they would expect to be black. Hispanic. Oops. Ugh. Alien. And then there's one more category. It's not listed for police officers, but it also, there's just an other. It says 2%. They would expect to be other. Okay, so you have to do that. I have to figure out what's the difference. Okay, next question asks how many degrees of freedom? Degrees of freedom is n minus 1, the number of categories minus 1. So how many categories do we have? 5. So it's just 5 minus 1, which is 4. So there are 4 degrees of freedom. Okay, so it says find the chi-squared and the p-value. So this is where you use the calculator. So first I'll do it with what most of you have. If you have the 84, just go to test, like we always do, and make sure there's 2 tests that say chi-squared. There's a chi-squared test and a chi-squared GOF. Make sure you're on the GOF. Oh, we have not done something really important. Don't do that really. Because the next thing it asks for L1 and L2, which we haven't done yet. Okay, so let's type our information into L1 and L2. Okay, so on the front of your notes, it said L1 had to be what? Right.
Observed.
Observed. Okay, this right here is our data for the expected makeup. So we need to figure out what we would observe. So we have to calculate that too. Out of the 26,181 police officers, we observed that 64.8%, I knew something you can't see, are white. So you'd have to multiply that. You can just use your calculator. We still need one more piece of data. What could be, how can we figure out the other category? Someone calculate what percent were other. Why did I do that? So 0.2 or other. It's not what he said anything. Okay, did you get the same as me? Because I'm not sure. Yes?
Yes.
Okay, so that's our observed values. That's the hardest part. Now we just type in the expected. Okay, now you should be able to run the test. Let's try it. So go to stats and then test. And just make sure you do what it says. The observed should be in L1, expected in L2, degrees of freedom was 5. And
What's it for?
semester.
Still doesn't work.
It still doesn't work. I know why though. I just remember it. Okay. Go back to your list. I just remember this. L1 is your observed values. L2 is expected, so it's like a theoretical value, so they can be decimals, but L1 is what you actually see. Can you actually have a decimal amount of police officers, people? No. So L1 you do need to round to the nearest whole number, which you can just look at the bottom and round it. So like the first one's 16,965. 3796. 5,000. Oops. 1. 367 and 52. Okay, now see if it works. The test itself is really easy. I mean, it's one button in the calculator. It's setting it up. Okay. There we go. That is right. Anyone else get something similar? The same? Same?
I don't have this.
Okay, I'm about to show you. Alright, so that's chi-squared. Is it off?
Oh yeah, but it's like it rounds to the same thing.
Okay.
It's just not.
And that's okay. It can depend on how you rounded your answers. Is your p-value the same?
Yeah.
0? Okay, and that's what's most important.
Oh, that didn't work.
So it said domain error.
Okay, domain error. Did you make it so that the first list was all whole numbers?
Yes.
I'll come back to you. Okay, people who I loaded just a second, I'll help you if you're having trouble, but first people who had a program, here's what you have to do. You have to go to programs, PRGM. Everything else starts the same, you still have to put it in L1 and L2. Then go to program, you might have other programs there, but look for DOS. You see it? And then you don't have to type anything in, you just hit enter. And it'll give you chi-squared, freedom, and p-value. Which really all you need is the chi-squared and the p-value. Does that work?
Yep.
So it's just as easy, it's just in a different place. Okay. Let's pause. Okay. So I told you if you're going to use a calculator, I want you to show the calculations for 2 variables using the formula. Okay, you can actually go back and do that after you've already calculated the chi-squared. That's going to be the easiest. So just look at your table. And the formula for yesterday is observed minus expected. So just start with the first one and do the observed minus the expected squared. And then it's divided by the expected. Okay, that's one term called term of the calculations. And then do one more. So the second one observed is the first value minus the expected squared divided by the expected. And you just put dot at dot. So it's saying that's where the chi-squared comes from. So you're just showing how it's calculated, even though you didn't really do that to calculate it. Okay, so now this is a statement conclusion. This is like always. If the p-value is low, reject the hoe. So what are we going to do? It's very, very, very low. So we're going to reject the null hypothesis. So if we reject the null hypothesis, that means we're accepting the alternative. So our conclusion in context is that police officers do not reflect the ethnic composition of today's youth, or of the city's youth. Okay. Sorry, that shouldn't have. Besides all the calculator errors, any questions on the concept? You see how it's the same as all our tests. We're just finding the p-value, just a different way of finding the p-value. So writing hypotheses and stating conclusions. Okay, this is the last one we're going to do. We'll go a lot faster. It's not as big in numbers. It makes it easier. So it says Fortune magazine collected the zodiac signs of 256 heads of the largest 400 companies. It asks, is the data evidence that successful people are more likely to be born under some signs than others? So first thing we're going to do is state the hypotheses. This one, it doesn't really give you a lot of information. It doesn't really tell you what we expect. But we're trying to see if it says if they're more likely to be born under some signs than others. So like, are they more likely to be a Taurus? Are they more likely to be a Gemini, or etc.? So the opposite of that, if they weren't more likely to be a certain sign, what would that mean for all the categories? So it's basically the same. You would expect them to be about the same in each category. So how can we write that? So you can say successful people are, we'll say born under all signs equally. We're saying all of them are about the same. And then the opposite would be that successful people are more, what we're testing for, are more likely to be born under certain signs. Okay, so it says if the births of executives are distributed uniformly, what would be the expected value for each sign? So distributed uniformly, that's the same thing as all signs are equal. That's our null hypothesis. Okay, so if there are 256 people in our sample, and we expect each category to be about the same, how can you figure out how many you expect to see in each category? There you go. You can do this. Just 256 divided by 12. This one's more like the Fruit Loop problem we did yesterday. We expected each color to be about the same. 21 and a third. Okay, how many degrees of freedom? 11. Good. It's just n minus 1. So there were 12 categories. subtract 1, and it's 11. Okay, so let's try again to do the test, find the chi-squared and the p-value. It's going to be a lot easier this time. The numbers are a lot smaller. L1 is what we observe. This time we don't have percents. It actually told us how many were in each category. So that's good. We can just type those in. 23, 20, 18, etc. Maybe I won't make a mistake. Okay, L2 is what we expect. So we expect each category to be exactly the same. And what number is that? Our 21.33. They're all the same on this one. See, much easier this time. Okay, now you just run the test. So stat, test, or program, find chi-squared GOF. L1 and L2 should be right. Our degrees of freedom is 11. It's not 111. Okay, so 5.09 for the chi-squared, p-value is 0.93. However, don't forget to show me two calculations. So just start with the first one. It's the observed minus the expected squared divided by the expected. And then do that for one more. So observed minus expected squared divided by the expected. And you're just, again, showing where your chi-squared comes from. That one like a fifth the time to the other one. Much easier. So state the conclusion. So can we reject the null hypothesis? You think 0.93 is low?
No.
No, that's extremely high. So we will fail to reject. And this part is just like all our hypothesis tests. When you fail to reject, then there is no evidence of whatever you're trying to prove. So in this case, there's no evidence that, to restate the question, that successful people are more likely to be born under some signs than others.